Welcome to the final part of the exercise series 9. I know it's getting very long, but well, see it as an advantage of being able to record classes. Normally in classes in the past years, we weren't able to see this many exercises. So really see them as, well, basically a step-by-step guide that you can put next to you when you're solving the function, these exercises, and can see where you're going wrong and that kind of stuff. Okay, so we're gonna make the last exercise together. And we're going to make exercise P, which is an investigation of the function fx is equal to x times ln x. Okay, so first things first, and this one is going to be a lot quicker than the previous one, I promise. So the first one, what is the domain of this? Well, x is not really restricting our domain, but ln x is, right? ln does not like, it does, excuse me, ln does not like, well, negative numbers, and also it doesn't like 0. So what do we say? Well, our domain is R plus, saying only positive numbers, and we exclude 0 from this domain. Okay, so then let's have a look at our roots. Well, our first root is where x is equal to 0. And then the other root where we could reach is where ln x is equal to 0, right? So here be careful though, because here we say x is equal to 0, but we excluded it for the domain, so we can cancel that one out and say, well, that one isn't part. So the only one that's true candidate is where ln x is equal to 0. So let's see where that is true. Of course, if you know a bit about logarithms, you'll immediately see where that is. But let's convert this. We can say we'll raise both sides to the power. We use our exponent on both sides, so we get e to the power of ln x, e to the power of 0. All of this cancels out, and we're just left with x is equal to e to the power of 0, or x is equal to 1. So that would be our root. Then let's have a look at our vertical asymptotes. Do we run the risk of dividing by 0 somewhere? Well, no, we do not. So there are no vertical asymptotes. Are there any horizontal asymptotes? Well, we can consider our function for x approaching infinity, because not negative infinity, because, well, it doesn't exist there, the function. Approaching infinity would just be infinity, so no horizontal asymptotes, no oblique asymptotes. Much the same reasoning tells us that there is no oblique asymptote. Okay, then we can already go to point number 4. Bring all of this information together. Well, and here it's the first time we see something new. We know that, well, our function cannot exist for values smaller than 0. So we can just scratch that out and say, well, the function doesn't exist there. And not only lower than 0, but also at 0 itself, it doesn't exist. So over here, it doesn't exist as well. Then we get a root over here, and we know it's 0 over there. And then let's see what this does. Well, if it's smaller than 1, this is going to become negative, and this is just going to be positive, right? So that means it's going to be negative. And then over here, well, it means this is positive, they're both positive. Means that our function will be positive over there. Okay, then let's take our derivative. So f accent of x, which would be the derivative of x, which is this 1 times ln x, plus x times the derivative of ln x, which is 1 over x. If we rewrite that, we get ln of x plus 1. Okay, then we move on to part 6 already. Where is ln x of 1 equal to 0? So, or in other words, where is ln of x? Let me rewrite that a little bit. ln of x equal to negative 1. Again, same trick as before. Raise both sides to the power, well, use the exponent of e on both sides, e to the power of negative 1. We can cancel these things out, and we get x is equal to e to the power of negative 1, or in other words, x is equal to 1 over e. So that's going to be the root of our first order derivative, right? Okay, then we can investigate the sign of this. I'll do it as such. We have x. Remember, our function doesn't exist all the way up until 0. And then here at 1 over e, something is going to happen. Well, our function here, f of x, is equal to 0. And then it's going to be, then we're interested in the values of these functions. So let's have a look over here. Well, we know that here it's equal to negative 1. So well, what is it if it's greater? That means that this 1 is still cancelling it out, right? If it's greater than 1, then 1 over e. So you can find that it's positive over here. You can just fill in whatever, right? A very large value over here, it's going to be positive, and then just over here, it's going to be negative. Okay, then what does this mean for our normal function? Again, our normal function just doesn't exist over here. It means that it's going down, and there it is going up. Then we can move on to point number 7. Here we need to take the second order derivative, which is, in this case, just the derivative of this thing, which is 1 over x. Does that have any roots? No, it does not have any roots, so it should prove to be quite okay. So let's do our extremum test. Let's fill in 1 over e, so f double accent 1 over e. We find that this is 1 over 1 over e, or in other words, equal to e, which is greater than 0, which tells us it's going to be a minimum, which we of course already knew because this clearly follows the shape of a minimum. Okay, now we have that, we can move on to finding the potential other roots of f double accent x. So the second order derivative. So where is f double accent of x equal to 0? Well, that never happens. There is no value of x for which f double accent of x is equal to 0. There exists non-x. Okay, meaning that, well, we'll still have to look at what the sign does, right? It means that it's just not going to change. So let's write a sign table. Yeah, I can write it just over here. So we get x, f double accent of x, and in this case, well, again, before 0 it doesn't exist, so, and at 0 itself it doesn't exist either, so that means not a problem. There are no asymptotes that we need to consider here. Up, and then over there, well, what's the sign going to be? Remembering our domain, we just only allow positive numbers, meaning that this is all going to be positive, meaning that the shape is going to look like this, right? Meaning that if you bring these two things together, it means we go down like this, and then we go up like this. Typical behavior for a minimum. Okay, all that's left to do now is to draw this once. So first and foremost, we know that we start over here. Let me take a different color. Careful, because 0 doesn't exist, so I'm gonna really exaggeratedly draw an open dot here. Of course, it's just to tell that 0 is not part of our solution. Then at 1 over e, we reach a minimum, and then here at 1, we have to cross the x-axis again. Okay, now let's consider what the signs of our function look like. So first, between 0 and 1, it's going to be negative, so we know that it's over here on this part, all the way, it's going to be here, and then we know that it is going to become positive after 1, and we know that it needs to respect this shape. So let me pick a different color. Well, it needs to be negative. We need to reach a minimum over there. Well, the only way to do that is by going down like this. If we follow our arrows over here, you see it descends like this, and it goes back up like that. We go back up. We hit our roots. Now let's see if something changes after 1. No, nothing changes at 1. It keeps this shape. It keeps rising. So we just can continue over here and continue the cup like that. So this would be our function f of x in this case, which is x times ln x. Okay, so this was the last full function analysis I'm going to do with you.